Research with the Smith Group focused on synthesizing 2-aminoethyl cinnamate for studying responsive liquid crystal elastomer materials. To begin, it's important to talk about liquid crystals, which are rod or disc-like molecules that have low molecular weights. We are interested in their ability to exhibit characteristics of both liquids and crystals, meaning that phase characteristics change with stimuli, which the image below shows that as temperature increases, the liquid crystal moves towards a more disordered state. Lightly cross-linking liquid crystals results in liquid crystal elastomers. Like the liquid crystal elastomers, or LCEs, can transition between ordered and disordered states, but their network structure gives them a rubber-like elasticity. With a stimuli like temperature or light, LCEs, with their liquid crystal units initially aligned in one direction, can exhibit large deformations. The leftmost molecule shows a main chain structure LCE, meaning the liquid crystal units were incorporated directly into the main chain, which is what we are looking for since the main chain pendants would amplify the deformation most. Once aligned, these molecules have great potential in a variety of applications, many offering impacts to the aerospace field. One area, shock absorption, looks at integrating the aligned LCEs into helmets for safety by using the LCE's soft elastic deformation response. Reconfigurable antennas look at sensing structures that can morph and pick up different signals in a controlled manner, using the shape-changing property of aligned LCEs. In the past, alignment has been approached through use of command surfaces and mechanical stretching. Command surface techniques generally resulted in very thin sheets of aligned material with limited initial geometries, meaning the final material lacked depth and thus functionality. More recently, producing aligned LCEs through 3D printing has been approached, with the result of improved design geometry, but still with limitations from alignment only following ink flow direction. Both of these areas are promising, but in order to move alignment beyond 2D sheets and printing flow direction, finding an alternate alignment method that is approachable and void of restrictions is crucial. Further, current techniques often require elaborate procedures and specialized equipment, which hinders accessibility and scalability of LCE alignment chemistry. Overall, the goal is to create mechanisms for aligning 3D material without any orientation restrictions. The process for producing the final material begins with synthesizing cinnamate derivatives. The cinnamate derivatives are then formed into dimers and irradiated with polarized UV light, and then added to LCE networks via azomical addition reactions. We decided to use cinnamates for our alignment approach because it has been demonstrated that they are plausible in bulk-mediated alignment and have shown to work in low molecular weight liquid crystals. Our goal is to easily incorporate the derivatives into LCEs and study their influence on material alignment. So what we want to do is work within the LCE units, but with the purpose of producing alignment intrinsically, rather than achieving alignment through a guest molecule. The amine to be added via Michael addition was synthesized in a two-step process that closely follows a patent procedure. The first line shows the first step producing the Bach-protected aminoethyl cinnamate. The second step is a Bach deprotection procedure to create the amine salt and ready the molecule for addition into an LCE. The project goals look at stockpiling 2-aminoethyl cinnamate hydrochloride, or AEC, and characterizing it. The AEC is a photodimerizable pendant that we will attach to LC oligomers in order to facilitate alignment. Then we want to continually improve and refine the patent procedure to develop a reproducible and scalable route for synthesizing the cinnamate while considering yield, purity, and reaction duration. Both FTIR, and NMR data taking were used to characterize the cinnamate synthesized. Melting point and purity calculations were also performed to further characterize this molecule. We wanted to show that the synthesis was successful, and we wanted to add characterization information to this generally unexplored molecule. Beginning with the patent procedure, we were able to find a scalable and robust route for synthesizing AEC. The AEC was characterized and produced with acceptable yields and trace impurities. In the future, we look to incorporate the synthesized derivatives into LCEs and study their effect on material alignment. A thank you goes to MSGC and team members Dr. Matthew Smith and Jacob Kowalski.